Okay, so we've got another video coming up on linear regression now. We've ran our three tests, or our four tests using three plots in four separate functions right now. Oh my gosh, three separate functions. What we're going to do before we start regressing on a really popular term that I don't think is useful are fair value gaps. Before we do that, we're going to just change all of these functions into one big test regression output. So I've already made that here, and this code is posted for free for everybody to paste into their own terminals whenever they feel like running these tests on their own. All I've done is take these other functions, test linearity, homoscedasticity, which is the same plot, test independence, and test normality. These are all just different plots, and I've put them all into the same one function. Now, what this does is it allows the main function just to be a bit cleaner, a bit shorter. So after we generate our regression output, we just validate the regression output, and it returns our same three plots. Just as a review, we can test homoscedasticity and linearity in the same plot that shows the relationship between predicted values and their residuals. If there is a fanning shape, that implies there is a heteroscedastic nature of your regression output, which means there's more variance with greater predicted values. And if there's a curved shape or a parabolic shape, that means there's a non-linear relationship between the two variables that you are regressing upon, or your feature and target variable. And now there's also a lag plot of residuals. So if one error is correlated with the error afterwards, that means that you're not regressing on functional or good data. If your scatter plot looks pretty random, like it does here, then there's no autocorrelation or the residuals aren't related to another, so you can move forward with your analysis. And then you want to make sure you get a nice normal shape with no skewing or no double peaks. It's a little bit more rare to have an abnormal distribution, but if you do encounter one, you want to be wary of that. For now, we have a pretty good output when we're using Tesla as our ticker, and we also have a generate output and validate regression output function. Super simple. So we're going to be pasting all of this code up until, actually we'll be pasting some of this in afterwards, but we're going to be testing the effectiveness of fair value gaps, both bullish and bearish. For anybody who stuck around to watch that video, which was one of my more viewed videos, I think, we have not only the existence or non-existence denoted as a 1 or a 0, we also have the magnitude of these fair value gaps built into our functions. So what we'll be able to do is assess whether there's a relationship between the size of a fair value gap existing and the magnitude of a price change following it. Let me pull in our data from the regression validation function, because that's the most reflective of what we will be using here. We can get rid of the relative strength index because we're no longer using that. We just have a 1-day shift and a look back period of 1,000 days. We're defining the bullish and bearish fair value gaps, and we also need to define the target. We're going to define the target before we define the bullish and bearish fair value gaps, because what I want to do is only have our data frame involve rows where these bullish and bearish fair value gaps exist. And the way we're going to do that is by we're actually just going to be making another function to filter the data frame for rows where the fair value gaps exist, both bullish and bearish. The reason I didn't want to just look at the relationship between bullish or bearish specifically is because those residuals would cut off at 0, or the scatter plots would cut off at 0, and that doesn't look super clean, and it's not useful for explaining their relationship. So we're going to define filter FVGs of the data frame And what we want to do is just return a data frame where if the data frame, this is a bit tricky actually. Yeah, there's two requirements. So we're going to put it in parentheses. Data frame bool FVG equals 1 parentheses, and then we're going to do this notation, more parentheses, and then data frame bare FVG equals 1. And that will just return the data frame where these two requirements are met. So we're indexing both. This is like and, put very simply, this just means and. Data frame bool FVG and bare FVG. And then I think this is in all caps. So when we get our main function, which is going to look a lot like our main function from testing the similarities between the RSI and close price movements. Instead of add RSI, we're going to be add bool. Oh no, just bool FVG and then bare FVG. DF equals bare FVG. Great. And then validate regression output. We are yet to import those, so we're going to do the same code from our regression function. So pasting in validate, and we also need to paste in generate. So these are longer functions, and they're only going to get longer. I warned you. Yes, and then strategy is what we're going to make as a global variable. Strategy equals we're going to need to make a separate column. Let me just run this so I can show you guys the data frame we have so far. Strategy for now, I'm just going to set to be volume, which is going to give us a bogus output, but it should make the data frame return correctly. What we need to do is create a column that shows the sum of values in the bare FVG value column and the bool FVG value column. So when a bullish fair value gap is present, RSI is not in the index. Where have I even mentioned it? Oh, features equals F, and then we're going to do that strategy that we just defined. Strategy. Good. Okay. Now, we have bearish fair value gap and bearish fair value gap value, and it's not a number when I forgot to only take in the values that we set this up. So data frame is going to be filter fair value gaps. Data frame equals filter FVGs of the data frame. So bool FVG I have with a capital, so this isn't going to work. Bool and bare is also capital in the filter function. Should be good now. Okay, now we have a nice clean data frame with 1,222 rows of instances where fair value gaps existed. Now, if there's a bull value, fair value gap, it's positive. Otherwise, it's just 0. And if there's a bearish fair value gap, it's negative. Otherwise, it's just 0. So what we want to do is create a relationship between these two values and the target, which we've defined here. So what we want to do is make a column that takes the sum of the bullish fair value gap value and the bearish fair value gap value as well. And that's going to be our feature variable that we are regressing on. And once we do this, you notice how we have 2 halves of the distribution of fair value gaps because we have bearish and bullish. We're going to put them together, and it's going to be one big bell curve. And our plots won't look like this anymore because they're chopped off at 0. So what we are going to do is... I didn't expect this to look so good. I might be doing something heinously wrong. I'll check it later. For now, I want to make a new column. So instead of filter FVGs, I'm going to rename this like prepare data frame for regression. So not only are we going to only be parsing the rows where fair value gaps exist, both bullish and bearish, data frame is going to equal this, and I'm just going to make it a copy. And then what we are going to do after that is do data frame both FVGs. Not probably the most insightful name. I didn't think about it very long. Both FVG is going to equal data frame bare FVG val plus data frame bull FVG val. And what that should do is give us a range of values. And I'm going to do plt.hist both data frame both FVG to show you guys what that output will be, and we'll call the title plt.title all fair value gaps. And I hope this returns a nice plot with a good clean bell curve of everything that we have so far. And we rename this function to be filter to prepare data frame for regression. And none type is not subsettable. What have I done wrong? Is the copy wrong? Oh, I just returned nothing. Data frame, and I am going to keep this as a copy. No, I'm not. Return data frame. Yeah. I'm going to make it a copy to get rid of that error, I think. Copy. It should be okay now. Yeah. Awesome. So all fair value gaps is for some reason above my other plot because I did not do plt.figure, which is an annoying notation that I always need to remember. Figure. Run the whole thing. Nice. So all fair value gaps are here. Most of them are really small, but some of them, you know, they're significant. What we want to see is a relationship between the size of the fair value gaps and the close price change tomorrow. So the target is here. We have it in percentage terms. There was a 16% drop on this day, it looks like. And most of the time, Tesla just moves between 1 and 3%, but it's a pretty volatile stock. So it's good to regress on. And we can do other days as well. I might actually just keep, for now, we can do S&P 500 for 500 days. 500, and then the strategy is now going to be both FVG. So our regression analysis will be, that looks very different. Because it's the S&P 500. Huh. That's interesting. I don't know why the coefficient is 17. Means I've done something wrong. Let me look. Oh, no, it doesn't mean I've done anything wrong. Let me change this to be, instead of 500, let's do 10,000. Do maximum, and then see if we get any heteroscedasticity. No, we don't. Okay. So there's no heteroscedastic relationship between our fair value gaps and share price movements over the course of one day in the following day. It looks like we've actually passed all tests when we do maximum amount of data available for the S&P 500. So the relationship between both fair value gaps and target. What you would want to see is a negative relationship, and even a moderately negative relationship. So when a bullish fair value gap exists, that means prices should come down to fill that gap. And when a bearish fair value gap exists, that means that prices should come back up to fill that fair value gap. This is the narrative that people explain often in paid courses that cost you $5,000. Oh my God. I'm explaining for free and showing you pretty objectively that that's just not the case at all. This plot just disproves everything that people make a lot of money selling you if you're not willing to take the time to watch these boring videos, which is insane. We can also just use the R-squared and correlation coefficient. Next episode, I will be getting more elaborate on those, on our regression outputs. I don't want to get too involved in the statistics. I know most of you are here for the application to trading. And you might be able to tell by now, but I'm mostly a statistics guy. I like that more than the trading itself. I think if you can master statistics, the trading will follow. Anyway, for now, the correlation coefficient is -7, and the R-squared is just garbage. So this looks like a strong correlation coefficient, but it's because of the units we're using. I multiplied the target by 100 to be in percent changes, but that just means that this is 100 times as strong as it was just. So there is a negative relationship. I'm going to get rid of the times 100. So the correlation coefficient is more representative of what's going on. So the coefficient is negative. It's 0.07. But that's not enough to be exciting. It might actually just have to do with this one strong outlier. I think I'm going to add to this plot a trend line. Yeah, so I just stole this line here from ChatGPT. It's the first time we've done this, but I'm getting a little bit lazy. Instead of showing you guys the process of getting it wrong and reading the documentation, I just asked ChatGPT for a trend line. And that's it. We now have a trend line, and you can see that there's not really a relationship, and the R-squared is also not super impressive. For now, actually, I shouldn't say there's not a relationship. There's not a statistically significant relationship just based on what we're looking at. We would know, or we would be able to take a strong guess on whether or not there was a statistically significant relationship, and we're going to be doing that test in a later episode. But for now, we can see that the relationship between the size of the fair value gap and the future price returns over 30 years of S&P 500 data we have how many instances to work with. We've got 2,639 observations. That's pretty strong. We have a valid regression test that passes all of the tests, and we see no real relationship. We can try this on other tickers to see if there's a stronger correlation, stronger negative correlation. We can do Duolingo, which is from the strong portfolio in Sharp research this quarter, and that's actually a positive relationship, I think. Yep, slightly positive, but still not really strong. I think the variance we find in the correlations here is going to be related to randomness, not tickers being more effective or less effective on this. So this is another negative relationship. Is it strong? Not really. It's less strong than actually the S&P 500 was the strongest relationship we've seen so far. It does pass all of our other tests. Perfect. And what if we did more than 1 day out? Will that violate our autocorrelation? Let's see. I think it will. Yeah, it does violate our autocorrelation issue. So we're going to stick to 1 day. And we're going to do one more ticker, and then I'll wrap up the episode. Tesla. Let's do Palo Alto, P-A-N-W. Palo Alto Networks. Negative relationship, not a super strong one, but we can't know exactly how strong until we get deeper into the weeds of statistics, which I will try to take you through at a understandable level in the following episodes. We're going to be talking about t-tests and p-values very soon. Congratulations for sticking around for this long. I know it might be interesting to you, actually. I found this super interesting for there to be no really strong relationship between fair value gaps and future returns over the next period. We can actually, if you want to see minutely or daily, which I actually do personally, let's do, instead of 1 day, let's do 1 hour. So we can do 1 hour hourly fair value gaps. Positive relationship on Palo Alto. Let's do TSLA. Hourly. Anything. Positive relationship. Passes all the tests. Nothing there. We're looking for that negative relationship again, and we'll do S&P 500 for 1 hour, and I'll go down to 5 minutes even with you guys. Negative relationship, but it's probably because of these outliers here. Still not a strong negative relationship. I know I'm speaking in general terms here, but we'll be validating what I'm saying about whether or not these relationships are strong in coming episodes. So now we're going to do 5 minutes. So some people say, oh, you're only testing on daily data frames. We only trade on minutely. Look, this is another positive relationship between fair value gaps and future price returns, because prices generally go up over time and fair value gaps don't mean anything. This is actually one of the stronger relationships we've seen so far. 0.4, 0.04, my bad. And it's just not impressive. It's really not. That's S&P 500, 5 minutes. And for the very last one, we'll do VMC. VMC, 5 minutes, check for a negative relationship, and it's just not. It's effectively random. And that's it. Now you know that fair value gaps are complete bogus. And I can imagine that if we test any other ICT concepts, order blocks, breaker blocks, whatever they call it, we'll find similar results. So congratulations, you're now a step smarter than one of the most followed trading channels in the world. I'm proud of you, and thank you for following along with my videos. Until next time, stay sharp.